All right, I'm back. We're on page 276. We're kind of in the middle. One of the keys to success in calculus is showing the work that leads to your conclusions. Obviously, we showed a ton of work. We learned the squeeze theorem, which is a big deal. It's later in the notes again, so don't worry about it too much right now. Usually a very contrived situation where it's very easy to pick out the limit on the left, the limit on the right, usually pretty straightforward. The next thing we're going to talk about something called relative growth rates. So relative growth rates are a little different, right? So what we're going to do is decide as x goes to infinity, what do these things do? So what I'm going to do, even though I feel like you could just look at them and know, I'm going to switch over to the calculator just to like graph them so that we're all on the same page. So this is our old graph. I'm going to put in a new problem, doc 4.1, graph page. All right, so let's look at x squared. Okay, not bad. We knew what that looked like. Natural log of x. All right, so this one, you should memorize this graph. If you didn't already do it in life, make sure this is a graph that you know instantly. Grows very slowly, very slowly. Logs in general are just like, they're the sloths of functions. They just grow incredibly slowly, but they do grow, right? Which gives an advantage over, for example, sine of x, which does not grow. It grows sometimes, right? It grows for pi, it'll grow and then it'll stop growing and like alternates. But it's stuck, it's trapped between -1 and 1. So it's never going to win in a race to infinity. It's just going to be stuck there. So far our champion definitely is x squared. Next up, natural log of x, and then sine is going to get crushed. All right, now we put in a new function, 2 to the x. 2 to the x grows really fast. Then suddenly x squared is growing faster than it, and that's kind of surprising usually. Let's change the window. So I'm going to change the actual window here. I'm going to make this go up to, I don't really know, like 100? Okay, so at a certain point, let's see what that point is. Is it 4? I don't know. Menu 8, 1, 4 for me, 3 for most people if you have CX2. Oh, it is 4. Why did I guess that? I don't know. I probably just knew. After x equals 4, 2 to the x is going to be above x squared for the rest of forever. If you don't believe it, you can trace, and then I need to trace all. Trace all. Let's menu 5, trace all. Okay, so F1 is the blue one. F1 versus F4 is what we need here. So you can see that, where'd F4 go? Disappeared. How useless. Oh, maybe it only shows when it's on the screen. Ooh, maybe. Anyway, I think it's compelling. I mean, F4 is just going to crush it, right? It's already like double what x squared is. And then it's more than double. And then next it'll be even more than double. And I don't even know what that means. But clearly our exponential is winning, then our polynomial, then our log, then our trig. So what we want to do is we want to know that. Like that's going to happen. And it doesn't matter what the exponential is. Eventually it's going to beat out a polynomial. It doesn't matter what the polynomial is. Eventually it's going to beat out a log. Doesn't matter what the log is. Eventually it'll beat a trig function. Trig functions here we mean sine and cosine. Tangent and secant and cosecant are insane, right? They have vertical asymptotes. Those you almost always need to look at a graph. What I'm going to do is go back to the notes and then fill in some notes here and go from there. So here we go. All right. So we looked at it and we saw that going as x goes to infinity. So let me go with the traditional black marker here. As x goes to infinity, what did we find? We found that y3 was the slowest. So I'm going to say y3 is going to lose to, the next slowest was y2. And then the next slowest was y1. And then the next slowest, the fastest, was y4, right? So what are those? We got trig is going to lose in a race to a log, which is going to lose in a race to a polynomial, which is going to lose in a race to an exponential. And that's going to happen every time. So these are relative growth rates. So that means that if you have a trig function divided by an exponential function, guaranteed limit will be 0 as you go to infinity. If you have a log divided by an exponential, you're going to get 0. If you have a polynomial divided by a log, you're going to get infinity because the polynomial is going to win the race. So these are generalizations, but they're generalizations that are good to know. Sometimes you want to be able to generalize. And at this point in your life, it's sort of the only way that you can do some problems. So let's see these, for example. I see limit as x approaches infinity of x e to the negative x, which like you can logic out a little bit. Basically, if you just try to like sub in, right? We're subbing infinity. So if I sub in, whatever that means, I'm gonna get x goes to infinity, so I get infinity. I get e to the negative infinity, which is 1 over e to the infinity. 1 divided by e to the infinity is definitely 0. If 1 divided by x goes to 0, then 1 divided by e to the x goes to 0 even faster because e to the x grows faster. So this would be infinity times 0. All right, what do we do with that? That's a pseudo-indeterminate form. It's not indeterminate. 0 over 0, infinity over infinity, those are indeterminates. This one we can change, right? So I'm going to change this into the limit as x approaches infinity. That didn't work. Oh my God, I made like 600,000 little dots instead of making an infinity sign. Limit as x approaches infinity of, well, why wouldn't we just do this? We would just do that. That's why we would do it. And now I have a polynomial divided by an exponential, and we just found out that exponentials win that race. So this is actually 0. And this was a poly divided by an exponential. And that's how we knew that, right? So relative growth rates, they're very helpful in these problems. All right, what can we do here? So this one, let's try subbing in again. So we're gonna sub in. So I'm putting sub in quotes because infinity, negative infinity, they're not really numbers. You can't really sub them into something. What you do, I like to say infinity is a journey, right? It's not a destination. So we're going as far as we can. We're gonna like think of the biggest number you can think of. Infinity is bigger by like an infinite amount. So we're going to negative infinity in this case. So if I sub in, I'm going to get negative infinity because x is going to negative infinity, so x goes to negative infinity. Then I get e to the negative infinity, which is e to the infinity. So look at this. This is not indeterminate. E to the infinity is enormous, bigger than you can conceive of, like bigger than your brain can conceive of. You cannot imagine this. This answer is actually just negative infinity. We don't need to do any more work. The limit as x approaches negative infinity of x e to the negative x is just negative infinity. That is it. There's no additional work necessary there. You didn't even need relative growth rates. Nothing to be done. All right, what the heck is this? All right. I think we're gonna apply the limit laws, right? So the limit laws say if each of the limits exists, then we can like break it up into separate limits. So I'm actually going to do that. I'm going to first look at e to the 3x is e to the x cubed, which is e to the x times e to the x, e to the x times e to the x times e to the x, right? So this first fraction I can actually break up into 3 fractions. I'm going to break it up as the limit as x approaches infinity of e to the x over e to the x times, so I'm only allowed to do this as long as all of the limits exist. If one of these limits doesn't exist, then I'm not allowed to do it and I have to go back and find another way. I bet it's going to work. Partly because I wrote the problem, but partly because like, you know, look at it, get a lay of the land. It looks like this is going to work out for us because I'm seeing a lot of relative growth rates here. X to the 5th over e to the x, and then plus there's a little bonus limit here. Limit as x approaches infinity. I always like to make that 1 over e to the x, just like easier to think of. All right, so we have all of these. All right, what is each of these limits? Well, the first one, so this limit is definitely just 1, right? Because that's actually the limit as x approaches infinity of 1. So this is 1 times The next one, I see a log divided by an exponential. I know by relative growth rates that the exponential is going to win by like a bajillion. So this will be 0. And now I still need to evaluate the other one, right? Because if the other one doesn't exist, I wasn't allowed to do this, and it's back to the drawing board. But when I look at this last one, I see a polynomial divided by an exponential. Exponentials are going to win. Exponentials win every race, pretty much. Factorials are actually faster, but they're not continuous, so we don't like talk about them. So this is going to be 0 also. So maybe I should have been underlining as I went. I don't remember what color these are. There we go. Okay, so far we have 0, right? 1 times 0 times 0 plus the last one is also 0. So overall, this limit is 0. So relative growth rates, it's an important idea. You eventually learn things that allow you to make it a little more formal than just thinking like, well, exponentials beat out logs, so therefore that's my answer. But for now, that's like all you can do. And so it's not a bad thing to do. It's a good thing to know, because even when you know the other way of doing it, you're going to look at the problem and be like, I already know the answer because of relative growth rates. Now let me work it out and prove it to someone, right? So I'm going to stop this video here and come back and, keep going. So I hope you are finding these helpful. Remember, you can always slow them down, speed them up, watch them again, never watch them potentially, and you'll never even know I'm saying this. But anyway, I'll see you in the next video.